So the rate of the chemical reaction is a measure of how fast the reaction either makes products or uses reactants. We could think of it either way, it's all the same. So in this illustration from the textbook, we have A plus B forming C, and they've illustrated it here with little shapes. This is a reaction that has a fast rate. Over here, X plus Y making Z is a reaction that has a slow rate. And if we compare them as time goes on, here at time 0, we only have reactant for both. As time progresses, we see that by just over 45 seconds, this first reaction has gone completely to product. It's done. Whereas this reaction over here is not finished yet. It's proceeding at a much slower rate. Any questions about that? This class is going to build on itself really quick. So as soon as I lose you, ask me a question, okay? So we use the concept of rate in everyday life. We think about the rate of speed, the rate of travel, so how fast a car is going. We usually measure that in something like miles per hour. It's distance traveled in a given period of time. So that's a rate. It's how much a quantity changes in a given period of time. So for speed, the quantity would be distance, and the period of time would be designated probably as an hour. So we could say that speed equals the change in distance divided by the change in time, or delta x over delta t. X representing distance, delta means the change in, and t representing time. So for a chemical reaction, the rate is generally measured in change in amounts, either of the reactants or products, divided by the change in time. So if we look at this gas phase reaction, hydrogen gas reacting with iodine gas to form hydrogen iodide gas. The change in the concentration of the reactants is going to be negative. Change in is almost always the final minus the initial. So we're starting out with a higher concentration of hydrogen, and that concentration is going to get smaller. So the change in the hydrogen concentration is going to be a negative number. The reactant concentration is decreasing. By convention, we always express reaction rates as being positive. Just like we always talk about the speed of a car as being positive. The direction, is north positive and south negative? I don't know. We would talk about direction in terms of north, south, east, or west. We don't say we're going, minus 50 miles an hour. We would specify that in terms of direction. So reaction rate here is also positive. So when we're talking about the change in reactant concentrations, we're going to put a negative sign in this equation so that when it's combined with this negative quantity of delta concentration of H2, overall we get a positive number. So it's the change in hydrogen concentration divided by the change in time. This would be the hydrogen concentration at T2 minus the hydrogen concentration at T1. Since this is larger than that, this quantity up here is going to be a negative number. T2 minus T1 is always going to be positive, and so this negative gives us a positive quantity for the rate. We could also express the rate in terms of the concentration of the other reactant. Any questions? We can also define the rate in terms of the product. So here we have one product. We could think of the rate in terms of the change in product concentration. As the reaction proceeds, the product concentration is going to increase. Its change is positive. So then we don't need a negative sign. We want the rate to be positive. The change in the hydrogen iodide concentration is positive. We're going to divide that by delta T. This 1/2 here is included because of the stoichiometry. For each 1 mole of H2 that we destroy, we're going to form 2 moles of hydrogen iodide. The rate needs to be the same, the quantity should be the same regardless of how we define it. So that's why we need the 1/2 here. Questions? So the rate of hydrogen iodide increases at twice the rate that hydrogen or iodine decreases. To have a single rate, we have to include that coefficient in here, so it's going to be 1/2 delta concentration of I over delta T. We can graph this information. We're going to do a lot more with graphing things and looking at graphs than we did in Chem 1A. Graphs are nice because they take numbers and they make them into a picture, which is much easier to look at and get things out of. I'm a visual person, visual learner, and so I like to be able to see stuff. So in this graph, we have the concentration in moles per liter of different things as a function of time in seconds. I'm still having that same issue with my iPad. So the green line here, it is green, isn't it? Yeah. Is the concentration of one of the products, the hydrogen concentration. So as time goes on, the hydrogen concentration decreases. And the hydrogen iodide concentration, the product, increases. It started out at 0, and as time goes on and the reaction proceeds, its concentration increases. The hydrogen iodide concentration is increasing twice as fast because of the stoichiometry of the reaction. Yeah. That's a good question. How would you tell that it's twice as fast? That's an excellent question. I would not expect that to be immediately obvious. I would expect that you could tell that this is increasing faster than this one is decreasing, just because they're not symmetrical to each other. Other than that, you'd have to look at you'd have to do a little bit of math to see that it's twice as much. Yeah, looking at the coefficients, you'll tell that the rate of formation of this is twice as much as that, twice as fast. Good question. Anybody else have any questions? The average rate of the reaction actually decreases as the reaction proceeds. Sometimes I get lost and I forget what I'm doing. So these are not straight lines, are they? They're curved lines. And so the rate of change, the slope of this line, it's becoming less steep as time goes on. The rate of the reaction is the slope of that line. We can look at data, just flat out numbers here. At time 0, there's the concentration of the hydrogen. At time 10 seconds, here's the new concentration of hydrogen. There's the change in the hydrogen concentration, the change in the time, and so we can calculate the rate. The rate is 0.0181. And so we do that for all of these other data points, and we see that the rate is getting smaller as time goes on. The rate decreases as the reaction progresses. Well, how could you get that off of this graph without, just making a table and doing all that math? Well, we can talk about an instantaneous rate. And so you could take any point on this graph. Here we're looking at this point, and you can draw a line that is a tangent to the curve at that point. And from that line, you can look at the change in the concentration from the beginning of this line to the end of this line and divide it by the change in time, and you can calculate the rate. So here's the one we were looking at earlier, change in hydrogen ion concentration. If we look at this point, this is at 50 seconds, and you look at this tangent line, you can find that the change in the concentration of hydrogen was 0.28. Actually, let's write that down. So, delta H, I'm so used to that delta enthalpy thing. Change in hydrogen ion concentration is minus 0.28. You get that from this difference here. Delta T for this tangent line here is 40 seconds. And you could draw that tangent line as long or as short as you want. If you're doing it off the graph, like with a ruler, old school style, then you'd want your line to be larger rather than smaller to have less errors. So then we can calculate the rate here. It's going to be negative delta H2 over delta T. My calculator's in here somewhere. 0.28 negative, oops, 0.28 divided by 40, change the sign. So that gives us an instantaneous rate of that at that point of 0.007. And the units on that would be molarity per second. So that's how you can find an instantaneous rate. What we're looking at over here, this rate is the average rate within this time period. It's not an instantaneous rate, but it's the average rate for the time 0 to 10 seconds. And when we look at this graph, from 0 to 10 seconds, there's not a lot of curvature in that line, but there's a little bit of curvature. The rate is not constant as time progresses. It changes. Any questions? We can generalize the definition of a reaction rate for a generic reaction. So here, we've got A plus B reacting to form C plus D, and we've got these lowercase letters in here as the coefficients, because they could be 1, they could be 5, we don't know. So we're making this out of variables so that it applies to all sorts of different things. So we could say that the rate of this equation is equal to minus 1 over A, the coefficient on this reactant, times the change in concentration of that reactant divided by the change in time. Or we could define it in terms of reactant B. Again, minus 1 over B, delta B over delta T. Or we could define it in terms of the products. Delta C, we're going to multiply by 1 over C. So that other reaction we had, H2 plus I2, made 2HI. What we came up with for that one was the rate was equal to, it's following the same form as these two here. Take the coefficient, which is 2, so 1/2. The change in that substance's concentration divided by the change in time. So if, yeah. Right. If you calculate the rate for one reactant or product, you don't need to calculate the rate for the others because at that point in time, the rate is the same because they are all part of the same reaction. That make sense? Well, the concentration does have an effect on most chemical reaction rates. We're going to talk about that. But at any point in time, the rate of reaction for A is the same as the rate of reaction for B, the same as the rate of reaction for C, and the same as for D, because it's all happening together at the same time. Any other questions? So we can, that's kind of what we were talking about just now. Knowing the rate of change of one species, we can see the rate of change of other species at that point in time, but we cannot predict what's going to happen to the future rate. How is it going to change? So this is an example from the textbook. Consider this balanced chemical equation, chemical reaction. So it says in the first 10 seconds, the concentration of iodide dropped from 1 molar to 0.868 molar. Calculate the average rate of this reaction in this time interval. The average rate, we're not getting an instantaneous rate because we don't have a graph to draw a tangent on. We're going to do the average by looking at the change in iodide concentration divided by the change in time. So for this reaction, the rate in terms of iodide we're going to have change in iodide divided by change in time. What else do we need to put in there? A negative. This is a reactant. The change in its concentration is negative. We want our rate to come out positive, so we need a negative sign. What else do we need to put in there? A 1/3. There's a coefficient of 3. So we need 1/3. And that comes from what we were doing here. So for this guy, it's going to be negative 1 over B times delta B over delta T. So that is the equation for the rate of this in terms of I minus. So the change in the I minus concentration is the final concentration minus the initial concentration. That's an I. Come on. 0.868 minus 1.000. So negative 0.132. And if I screw up, please let me know. So that's our change in iodide concentrations. So we get the minus 1/3. Up here we've got negative 0.132 molar. What's the change in time? 10 seconds. It's the first 10 seconds. So that's from 0 up to 10 seconds. Divided by 10 seconds. Yeah. Yeah. There, I made it into a 3, but actually, no, I screwed up, and I don't know why I wrote a 2. Thank you. I'd like to say I was just seeing if you're paying attention. Okay, so then we do just a tiny bit of math here. and I'm getting 0.0044. And that should have a 0 after it because there should be 3 sig figs, and the units would be molarity per second. Any questions? Okay with that? Okay, part B. Determine the rate of change in the concentration of H plus during this time interval. So before I forget, we just determined that the rate was 0.0440 molarity per second. So this is asking us to figure out what is the rate of change of H plus. So that would be delta H plus over delta T. Well, does this rate only apply to the iodide? No, it applies to the entire reaction. That's the rate of the reaction as a whole. Could we express that rate in terms of hydrogen ion concentration? Yeah. So that would be what? Do we need a negative sign? Yeah, because this is a reactant. Its concentration is going down. So we need a negative. Do we need a fraction? Yeah, 1 over 2. And then the change in hydrogen ion concentration divided by the change in time. This is what we're asked to find. Not the rate of the reaction, the rate of change of the hydrogen ion concentration. There's a very subtle difference there. Well, we have a perfectly good equation here that we could solve, right? So we just need to get rid of this 2 and this negative sign. So we're going to multiply by 2. And we get a negative, and so we're going to get minus 0.00880 molarity per second. So why is that rate of change negative? Because the hydrogen ion concentration is going down. Its rate of change specifically is negative. The rate of change of a product would be positive. But when we talk about the rate of a reaction, it's always positive. So this is one of those kind of confusing things where sometimes the negatives are important and sometimes they're not. Any questions? Let's do another one. Predict the rate of change in concentration of H2O2 and I3 minus during this time interval. This is the same problem, right? So it's still true that during that time period, the rate is 0.00440 molarity per second. What's that going to equal in terms of the hydrogen peroxide, H2O2? Just negative delta H2O2 over delta T. So this one it's negative. It's the same. Because it doesn't have a coefficient. And what about the I3 minus? Well, if we write the expression for that, it's going to be positive, right? Because it's a product. So the rate for that one is plus 1.0044. Its rate of change is increasing. Any questions? So how do you measure a reaction rate? In order to do this, we have to be able to measure the concentration of at least one of the components, one of the reactants or one of the products in that mixture as a function of time. And that's easier said than done in many cases. There's two ways to approach this. If the reaction is fast, if the reaction is going to go to completion in, say, less than an hour, we better monitor that change constantly. So we'll do continuous monitoring. If it's a reaction that's going to take like 3 weeks to finish, then we don't need to sample the concentration continuously. We could look at various time intervals. We could maybe do it every hour or every day or something like that. So there's continuous or there's sampling at intervals. How do you measure the concentration of the reactant or the product without messing up the reaction? One technique is polarimetry. That's measuring the change in the degree of rotation of plane polarized light caused by one of the components. Scientist, I forget his name, he's in your textbook. One of the scientists who did the initial research in this area looked at the hydrolysis of sucrose into glucose and fructose. Those sugars rotate light. And so you can get a good estimate of the concentration by looking at how much does the light get rotated. So you can do that. Obviously, you can't do that with everything. You have to have something that's going to rotate the light. Another technique is to use total pressure. If you have a reaction occurring in the gas state where the pressure is going to change, you can look at the overall pressure. So here, 2N2O reacting to form 2N2 and O2. So if this is occurring in a closed container, you're starting with 2 moles of gas, you're ending up with 3 moles of gas. That's going to cause an increase in the pressure. And so you can measure the pressure, and that allows you to calculate the concentrations of the reactants and products. Again, that doesn't work for everything. Nothing works for everything. Spectroscopy. And this is one we're actually going to do in lab. Spectroscopy measures the amount of light of a particular wavelength that gets absorbed by one component over time. So we can look at something, I think the one we're going to do has a blue dye, blue food coloring actually. And you can use a spectroscope and it'll measure how much light is absorbed by that blue dye. When the solution is very blue, it's absorbing a lot of light. As it gets paler and eventually turns clear, it's not absorbing any light. And so the absorbance is related to the concentration. If we look at this reaction that we've been dealing with, iodine gas has a color to it. Anybody know what color it is? It's purple. Iodine as a liquid is brownish, but iodine in the gas state is violet. It's very pretty, actually. Hydrogen gas is colorless, and hydrogen iodide is also colorless. So in this reaction, we can look at the disappearance of the purple color. So a spectroscope or a spectrometer works this way. We have some source of light. The light is passed through a slit, so we get a narrow beam, pass it through a monochromator, basically a prism, so that we can select a single wavelength of light. We pass that single wavelength through our sample into a detector. The detector gives an electrical signal to the computer. The computer says, here's your absorbance. And so we can monitor the decrease in iodine concentration by looking at how much light is being absorbed. Any questions? So very simplified. But for most instrumentation, the important thing is just to have the overall idea of what's going on, because the specific details vary from instrument to instrument. So spectroscopy could be used for continuous sampling. You could have the computer continuously monitor the absorbance as a factor of time. How are you going to do periodic sampling? There's something that's really slow. I'm having an argument with my... There we go. Well, one thing that can be done is you can take an aliquot. Aliquot is a fancy word for sample. An aliquot is a sample from the reaction mixture. Take those aliquots out at specific times and analyze them. We analyze those quantitatively. That analysis could have many different forms. It could be a titration. You could take a small sample out of the reaction and titrate it if you're looking at an acid or a base or something else that could be titrated. You could do a gravimetric analysis where you precipitate it and measure the mass of the precipitate. Or you could use something like gas chromatography. In gas chromatography, you could take that aliquot and inject it into the gas chromatograph and identify different components at the same time. So here's a very basic overview of how gas chromatography works. So we have a carrier gas. Often this is something like helium. And helium is running through this injection port and into a column. This column is a very narrow tube, often many meters long. And then the gas passes out through the detector. The pointer is gone. Fine. You can see it. It's labeled, the detector. The detector sends signals to the computer. So the gas passes through the detector, and the detector will give very little signal from that carrier gas. So you take the aliquot that you've taken out of your reaction mixture, you inject it here, and then that sample goes through this column. You should have done or learned about chromatography. In my section of 1A, we did some paper chromatography, where we took some ink on a piece of filter paper and we set it in I'm losing my words and my voice. Beaker, that's what they're called beakers, and used ethanol and water or acetone. And as that crept up the paper, parts of the ink moved quickly and parts of the ink moved slowly, and we could separate colors. It's kind of trippy to see this black ink give us red, yellow, and blue bands, right? Like, wow, didn't know those were in there. Yeah, you can do it with leaves. You can make some crazy cool colors from spinach. It's really awesome. But that's what's happening here. There's a stationary phase, the inside of the column, and there's a mobile phase, the gas that's going through. And the different substances in your aliquot have different affinities for the column and for the carrier gas. And so when everything is set up correctly, they will become separated. And so what you'll see is a series of peaks as they come off the column. And so you can measure the area under the peak, and that correlates to the concentration of that substance. So you can take actually a very small aliquot from your reaction mixture, inject it in the gas chromatograph, and get some results fairly quickly. Yes?
So you're taking it in certain intervals, right?
Yes.
So then you would have multiple aliquots that you would
Right.
find.
Yeah. Yep. So, maybe you're going to do this every 10 seconds or every 10 minutes or every 10 hours, whatever's appropriate for the rate of your chemical reaction. One of the tricky things about taking aliquots is in your aliquot, you've got both of the reactants present. What's to keep them from continuing to react? Nothing. You got to do it quickly. So you have to analyze the sample right away or do something to cause the reaction to stop, quench the reaction or freeze it or something. But there's all these tricky little details that mess things up. The nice thing about a class like this is we don't usually have to worry about those messy details.